When we started designing Elastifile's file system, we wanted it to be enterprise grade, to be able to run both in the public cloud and on-prem and between them, and to have consistent and high performance. That means we need to support hundreds or even thousands of nodes, which is the size clouds can reach. In order to achieve that, we wanted to create a software-only product that doesn't require any special hardware like NVRAM, because installing special hardware at such scale is a very complicated business, and in a public cloud, it's even harder to ensure that you have specialized hardware. For Elastifile's file system to be enterprise grade, it needs to ensure consistent high performance, especially ensuring low latency of all operations, and to support different data services like snapshots and deduplication of data. In addition, Elastifile's file system is required to work well in noisy environments. There are a few reasons for this. First, public clouds are noisy. We don't know what's running on the system. We don't know how the network is configured. Second, both in public and private clouds, there's consolidation of workloads, which means that we have multiple different workloads running on the same system, and one can affect the other. This, on the one hand, is a major benefit of having clouds. On the other hand, it creates noisy environments which we want to be able to work well in and provide consistent performance. And third, in large installments, we're bound to have different types of hardware, different types of servers, different types of SSDs, and that all creates additional noise. So we wanted Elastifile to be optimized and to work great in all of these different noisy environments. Also, there are different topologies used in data centers, and then when we designed Elastifile, we wanted it to scale well for these different topologies. There's the hyperconverged topology, in which the compute and storage are co-located and they scale together, and the dedicated storage mode, in which the compute nodes scale differently than the storage nodes. And Elastifile was designed to support both topologies. So what do we have so far? We have a file system that needs to scale to thousands of nodes, needs to scale in different topologies, needs to work in noisy environments, and needs to support advanced data services. All of this while performing high IOPS and low latency consistently. Kind of cool, right? So we set out to design a file system that will achieve all that. First thing was to overcome legacy architectural bottlenecks without using special hardware like NVRAM. In order to do that, Elastifile was created to have a truly distributed metadata. Each file or directory can be owned by a different node, and this ownership can migrate according to workloads, conditions, and requirements. This fine-grained and dynamic ownership allows us to scale linearly both in data and in metadata operations. To handle noisy environments, the data can be distributed anywhere in the cluster. When an I/O is received, the node can decide where to persist it according to whatever considerations are important in that time. Not only can it choose where to write the I/O dynamically, it can also cancel or change its mind in case that I/O is taking too long, and then the server can relocate the data and persist it in a different place, overriding the previous write. This allows Elastifile to adjust for both low rate and high rate changes. For example, if the customer has decided to add VMs to some server, making it slower, or if a node has failed or some workload has peaked and caused some of the nodes to be slow. Elastifile adjusts itself dynamically and allows for the consistent performance to continue. A file system must be strictly consistent. Sometimes this is called strong consistency. Usually such consistency is derived or achieved by using algorithms like Paxos or Raft. However, Paxos and Raft are not geared towards high concurrency, and in our case, we need an algorithm that is both supports high concurrency and low latency. For that, we developed our own homegrown consensus algorithm, which we call Bizur, which is the Hebrew word for distributed. This algorithm, the Bizur algorithm, is geared toward low latency, high concurrency operations. Bizur is one of the major facilitators of our fine-grained, dynamic, strictly consistent ownership model, which allows us to scale metadata operations. We mentioned before that we want to support dynamic topologies and to be able to scale in different topology models, for example, the hyperconverged or the dedicated storage server. In order to achieve that, we designed Elastifile to have different services that can scale separately while retaining specific relations between them. The main services are the data services, the metadata services, and the protocol services. For example, in the hyperconverged environment, each server runs all three services. In the dedicated storage topology, different services are executed on different nodes. As part of designing for cloud, we consider virtualization as a first citizen. For example, in hyperconverged mode, by co-locating the metadata service with the user's workload, we can reduce a lot of the latency and the chattiness of file-based protocols. Specifically, read-only operations like get attributes, which occurs a lot in NFS, can terminate without even going out on the network, reducing the latency of this operation, and we reduce the total work of the cluster. As you can imagine, building a file system that is scalable to thousands of nodes, provides consistent performance in noisy environments, and is enterprise-grade and supports advanced data services is challenging. We are proud with what we built, and we're very excited to bring it to market.